Okay, the first thing we got to do is define two terms, distance versus displacement. Distance is a term that has magnitude only. It's what we call a scalar quantity. So I walked 1 mile, boom. It doesn't give you any directional information. It just gives you a distance. Whereas displacement has magnitude and direction. And so this time you would say I walked 1 mile at 45 degrees, or I walked 1 mile northeast, assuming that's 45 degrees right there. Now where this gets interesting is if I make the problem a little bit more complicated over here in blue. So up at the top in blue, let's say I walked 1 mile and then I changed direction and I walked a half a mile over here. I would say my distance is the sum of the two, 1.5 miles. Whereas if I'm talking about displacement, and I walked 1 mile, and then I turned a corner and I walked half a mile, my displacement is not 1.5 miles. My displacement is represented by this dotted vector, and it would be, just eyeballing it, it would be a little over 1 mile and a little less than 1.5 mile. That's the difference. And so in order to solve this, you need to do a little bit of trigonometry. And don't worry, if you haven't done trig in a while, we'll cover that in due time. But why this is important is because distance leads to a term we call speed. Speed is just distance over time. So if I walk that 1 mile in 1 minute and there's 60 minutes in an hour, I would say that my speed in that case was 60 miles an hour. I'm just giving the magnitude only. That's what we call speed. It's just a scalar quantity, magnitude only, no direction. Whereas using displacement leads to what we call velocity, which is a much more interesting term. Velocity is displacement over time. So now I would say I went 60 miles an hour at 45 degrees. So why is this important? Because I can have negative velocity. I can only have positive speed because distance is always positive. I went a mile this way and then I went 2 miles that way. Well, the distance is always positive, so the speed is always going to be positive. Whereas displacement can be negative. If I'm defining distance going to the right as positive and distance going to the left as negative, I can have a negative velocity. Now, this shows up all the time on homework problems. You'll see problems where, let's say, a switch car, a railroad switch car, goes that way for a while and turns around and then goes that way for a while and then goes back like that, and it'll say, what is the distance that it traveled? In that case, you'll add up all three, this plus this plus this, and then it'll say, what is the displacement? In that case, you just need to know where he started and where he ended up, and that distance is the displacement in that case. So it's a very common homework problem. So now let's take a look at velocity. Average velocity is defined as the displacement over the time. So it would be x2 minus x1 over t2 minus t1. And it's important to note that this is average velocity we're talking about. So we put a little bar over the v like that. So let's take a look at an example, a car driving along a road. We're calling this point 1 here 0 meters, and we're calling point 2 1,200 meters. So it's going to travel 1,200 meters. Time 1 is 0 seconds. Time 2 is 60 seconds. What is the average velocity of the car moving along that street? You just plug in the values here. You put your 1,200 here and 60 there, and you get an average velocity of 20 meters per second, and that's average. It could be going fast here and then slowing down here and then speeding up. The problem doesn't tell you that. All it tells you is the total distance traveled and the total time. So you are dealing in average velocity. So now let's turn the problem sideways and do it in the y direction. Let's say you get mad and you climb up a 5-story building and you throw your physics book off the top. So we're calling the building height 20 meters. And so we have y1 up here at 20 meters and y2 down on the ground at 0. And it takes 2.02 seconds to hit the ground. So we're calling T1 0 and T2 2.02. So you calculate average velocity in the same way. I'm just using delta y in the numerator this time. Plug in your values, and we get a negative average velocity because of the way I defined the problem. I defined the ground level at 0 and the top of the building 20. I could have done it the other way around and we would have ended up with a positive velocity, which is okay as long as you keep things consistent in the problem. So again, it's important to realize that this is the average velocity. Obviously, it's starting out at 0 velocity, and just before it hits the ground, it's traveling very fast. But the average velocity is minus 9.9. Okay, what about acceleration? Acceleration is defined as a change in velocity over time, like this. So let's take a look at our car example. We're calling that position 0. It's traveling 1,200 meters. Time 1 is 0. Time 2 is 60 seconds, same as before. Velocity 1 is 0, and velocity 2 is, the final velocity is 40 meters per second. So you would calculate the average acceleration like this. Plug in your 40, plug in your 60, and you'd get an average acceleration of 0.67 meters per second squared. Notice your units in the denominator, the time is always squared. And let's take a look at the book example again. Same height for the building, 20 meters. We're calling velocity 1 0, and velocity 2 I'm giving to you as 19.8 meters per second. Same time, 2.02 seconds. Plug your values in to the formula like that, and the average acceleration of the book is given as 9.8 meters per second squared. Again, notice the time is squared in the bottom. Okay, so where this is all leading is what we call the 5 equations of linear motion, the most important thing in the chapter. So we've already talked about equation 1, which is velocity, and equation 2, which is acceleration. And equations 3, 4, and 5 are derived in your book. There's nothing new. There's no new information or mystery about equations 3, 4, and 5. They're just simply derived from equations 1 and 2. All they are is just rearranging and combining equations 1 and 2 in different ways. But the beauty of these is that depending on the information that you're given in the problem, you look at the 5 and you pick the equation that matches the fact pattern. So if you're given the time and the acceleration and the initial velocity, you use equation 3 to solve the final velocity. Or if you're given the time here and here, and the acceleration and the initial velocity, but you don't know the final velocity, you can still calculate the distance here, and so on. So these are very, very important. We'll be using them to solve homework problems for several weeks. I would highly recommend that you write these down on a post-it note, or just write them on the inside cover of your book, or find where your book covers them and dog-ear that page, because we're going to use them over and over again.